So where we were, yeah, so work on it. And if your guys are having a hard time, come and talk to me. So I went and found Jackie today. I mean, we had a nice chat. He's taken a course in a bit from me, but we haven't, it's the longest chat we've probably ever had, just the two of us, bonding. And I looked over some of his slides today, and he definitely does things different than I do, right? You know he does. He covers the debugger, right? I haven't touched the debugger, in 50 years. So I haven't covered the debugger. So I asked him, how are we doing? And he says, no, you cover your way and I'll cover my way and we'll make it all blend. All right. So if you are taking it from me, you'll be more ready for 3101 than the other students. And if you take it from Jackie, you'll be more ready for your coding courses. And that's just the way it is. Yes? The joint parts. Yes. So if you haven't heard, all the programming tests, anything doing with coding, I'm not involved in, right? So it all has, Jackie's doing it, and he gave you these practice things, and then the lab test is supposed to be similar to, I said to him today, he said, if you've done these practice ones, will you be okay? And he said, yeah, if you know how to do the practice ones, if you could, in fact, if you want to test yourself, take the practice questions and change them somehow, right? Remember, I made up new versions of the knapsack problem. Am I returning the set of solutions? Am I returning the best solution? Am I returning the binary, right? And sort of say, what do you have to change in those cases, right? Think about little ways of changing it, and then sit in front of a computer without any notes and see if you can do it in 60 minutes, right? I mean, that's what you have. And different people have different skills, right? I know for me, I'm good at the math, so I would have the algorithm down, and I would be struggling to memorize the Java syntax, right?
The main concern is that 60 minutes, not like the problems or like, so that's my concern, like those three tasks which possibly could be a little bit, like during the test, kind of harder. So that's the main concern.
Yes. Yeah. So what the test will be, it will be similar to what you've done already, tweaked a bit, and you have to code it up by yourself in an hour without any notes, and which I don't approve of. Yes. I don't know. Yes, let's find out. Let's find out. To me, starter code would be tremendously good, right? I've had co-op jobs where I'd say, I don't know C, I don't know the programming language, and they said, well, take a week and read the manual. I don't need a damn manual. Give me a piece of code. And then I need to do this. What's the format for a loop? What's the format, right? So if you give a little bit of code, then hopefully there's enough code that it tells you how to do a loop, right? Where do you need a semicolon, right? So maybe I'll talk to him about giving you a little bit of starter code, if nothing else, so you remember the syntax of a for loop, right? You good with that?
I took at 2030 with Jackie.
Uh-huh.
If the format going to be the same, I think we're just going to get like the JUnit test.
You're going to get what?
just those like test cases, and then based on that.
Oh, right, and no code.
Yeah.
Right,
I think
right.
it's gonna be the same.
Yeah. Okay, now the written test, that's Jackie. All right, so what do you need? What's the written test is 100% me. All right? And he told me to keep things secret, and I've never been a secret person. Let me just tell you, no TA hours are assigned to marking it. All right, don't tell anybody, but it is. All right, so I got to come up with such a test, and I would have said absolutely crazy to that, but you know, we had strikes all the time, right? And during the strike, I made up 2 exams in multiple choice, and I think I did a great job. They were hard, but it tested the material, right? How to study for that? Well, you got to know what I'm passionate about. You know, I'm passionate about loop invariants. I'm passionate about not micromanaging your friends when you do recursion, right? Could we do a little bit of code? I don't know how we would do it multiple choice, right? So the truth is, I haven't done it yet, right? You'll get much better answers from me after I've actually made it up, right? Because I haven't thought about it, right? Everybody good? Yeah. You have previous ones, and I haven't, let me read the previous ones. I mean, the advantage of me not giving them to you, quite frankly, is that it was more than 5 years ago and you would have a hard time finding them. And if I was lazy, I could give them to you again, right? So that's the resistance. But let me at least read them. I haven't read them in 5 years. All right? Yes. Yeah. You want to go back to it?
You're not switching files, it's just changing pointers, right? It's one thing zero now, and who doesn't point to anything.
Yeah, you got it. What do you need? You need the 4 to point to nothing. You need the start pointing to 5. You need 6 pointing to 0. No, that's the joy about linked list is the node never moves, right? You're never actually copying a value. It's just playing with pointers, right? That's why you need a picture like this. And you say, what pointers do I have to move? And how do I move them, right? In fact, you saw what I did was for each pointer that needs to move, I wrote the code for it. And then I saw if I do them in this order, do I drop somebody, right? And you make sure you don't drop anybody, right? Each move in itself is just following the little things that we talked about in class. And then you do it so nobody drops, right? And you might need a temporary variable to hold something, right? Does that make sense? Any other thoughts? Okay. All right, so we're doing more. So what we're going to do today, so did I say that? Yeah, he said, just keep doing what I'm doing. All right, so if anything, if you take 3101 from me, you'll see some of the exact same slides, right? Because that's how I just copied them. I tried to dumb them down a little bit, but more or less, it's the material, right? So here we're talking about these complexity classes, right? Remember we did constant time that doesn't depend on the input, right? And we did log n time, linear time, n log n time, n squared, n cubed, 2 to the n, right? And so what we're going to do now is, in fact, when I first started teaching, I made more and I covered this topic more and more because students we're understand. Well, sorry, I'm realizing now students don't understand anything, so I should never panic when they don't understand it. But I made more and more slides on this, and I've cut them mostly out. But this is just a quick. We're trying to classify functions, right? So it's just like you would classify. Well, you split into mammals and reptiles, right? And mammals split into, right? So here we're taking functions and classifying them in these different groups. And it's a little bit of a lie in that there are functions that are in between, but they rarely come up in our life, right? So if you want, you can think about who's in between, but it really doesn't matter because they don't come up, right? And this is how I name them, right? What's theta of 1? Well, you can give a lower constant and an upper constant. Maybe your lower constant is 0, and your upper constant is 5. And for every sufficiently big n, the running time is between 0 and 5, right? That's what it means. It can go up and down, but it's between 0 and 5, right? And so what is this? This is log n raised to a number that's some constant, right? Log raised to the power of 17, right? What's this? This is a polynomial. It's n raised to the power of some constant, right? And you might say, well, what about n squared plus n, right? What's the constant? Well, the low order terms all can hide in here, right? All can hide in the fact that is it 2, is it 3? Doesn't really matter, right? There's some constant. If it moves somewhat between, right? If you say your function was n squared plus 1 billion n, right? Now, when n is small, the billion n's going to matter, right? But then as n gets bigger, the n squared is going to take over, right? And that's kind of where we can have the fact that this theta wiggles a bit. And that's okay, right? And then what's this? Oh, yeah, so this one is exponential. Well, it's 2 to the linear in n, right? So many things in life are that, 2 to the linear in things. But if you really want to get scary, 2 to the polynomial, right? And I don't even know if those are good names to differentiate this and this. Doesn't even matter, right? Well, double exponential. Yeah.
So the n factorial, let's say, would be between x and double.
Yeah, n factorial is, well, it definitely goes in, can fit in here, but it's bigger than that. Yeah, it's kind of n times 2 to the n. I mean, well, there are approximations of it, but it's bigger. N to the n, right? It's like n to the n. I mean, certainly n to the n is an upper bound. All right, so what are we doing? Right, and this is just saying, what does this arrow here say? That you give me any fixed constants like n to the 5 and any coefficients in front, they don't matter because once n gets big, these guys, they just fall in this order, right? So here the polynomials can be split into linear, quadratic, cubic, right? Quint something. And right, so here's somebody that lives in between, right? This guy is bigger than n cubed, and it's smaller than n to the 4th, right? But it lives in there. Yeah, we won't get into that. Right? why isn't the log absorbed? Is because it grows, right? It's not a constant. The theta, you can think about the theta as some constant, right? That wiggles, a wiggling constant, right? It's bounded between 1 and 5, right? So log n is not a constant. Right? On the other hand, see I have into the theta. The theta is up there. And the advantage of that is that the wiggling is in the exponent, right? Because the wiggling in the exponent is, well, this one's clearly a polynomial, right? It's into the 2. And this one here is clearly smaller than into the 4, right? So this guy here is bigger than into the 2 and smaller than into the 4. So then that theta up there, maybe it wiggles between 2 and 4, right? But I don't care if it wiggles a bit. Right? Does that make sense? Did you follow that? Right? Let's go back up here. This log can't be absorbed into this theta because it's asking for a constant, right? But if you go over here, this log plays, you can think about it as playing with, this isn't into the 3, this is into the 3 plus something really, really little, right? It's not into the 4. It's bigger than into the 3. All right, so this is into the what? Something bigger than 3, less than 4, right? And that gets all, this log can hide in this theta. You know what I'm saying? Everybody kind of get that? And why is this useful to you? It's because I'm fundamentally lazy. And I don't want to figure out these log factors, right? I want to hide them. So you want to know what you can hide and what you can't hide, right? And you can't hide this log, and you can hide this log into there, right? Does that make sense? And then here, this exponential one, well, we can hide a whole polynomial inside there, right? So this is 2 to the some constant times n, right? Well, what is this? The constant is 4. Well, you can kind of think this is all bigger than 2 to the 3n, right? This hurts you. Dividing by a polynomial, I'm not saying it doesn't hurt you, but it doesn't hurt you moving. This is still way bigger than 2 to the 3n, right? Because the exponential part matters so much more than the polynomial part, right? Exponentials, 2 to the 4n versus 2 to the 3n, there's a huge difference between them. There's a factor of 2 to the n between them, right? So this measly into the 100 just doesn't matter about this being a 4 or 3, right? So it can all get eaten into here. All right, does that make sense? Yeah, I don't know what that all was. All right, so you did this in 1019, right? How do we do this? We drop the low order terms, and then we drop the multiplicative constant, and you get that, right? And here, I'm using, often in computer science, we use BigOh because we only want an upper bound, and this means you have a lower bound as well. All right, so here's a bunch of numbers. I mean, this would be a great multiple choice question. Which of these functions are polynomials? Yeah, anybody want to reject any of them? What would you reject if you said you were going to reject something, right? We kind of said they're all, right? They're all polynomials, right? Which of these are exponential, right? They're all exponential, right? And all right, this is just naming these words again, right? The theta is bounded from below and from above. Omega is bounded above. Oh, no, big O is bounded above. Omega is bounded from below. Little o means F is actually smaller than G, right? By more than a constant. F, in fact, what we do is you look at G divided by F. The limit is G divided by F goes to 0, right? Because F is really smaller. So is it G divided by F or F divided by G? F divided by G goes to 0, right? Because F goes, it doesn't grow as fast as G, right? And then this is the opposite. This is really growing bigger. All right. Do you guys, did you cover this first order? No, you didn't. All right. So this, it looks scary, doesn't it? And it's the formal definition of this. And we have slides at the end of this set of slides in which I teach you a little logic, because my experience is most students don't get it. All right. So let's do that now. I like to play a game, right? There's one guy trying to prove this statement is in bounded by G, right? Big theta of G. So one person is trying to argue yes, and one person's trying to argue no, all right? And the person who argues yes, he starts off here and he gives you right? How do you prove that there exists a C? Well, you give it to me. You tell me what your your small c is. You tell me what your big C is, right? And then I tell you, well, we talk about sufficiently big N, right? What's my definition of sufficiently big, right? So I give you N naught. And then the adversary who's fighting me gives me a bad N, right? And then I win if this is true. All right? So let's cycle through that again. What are we trying to prove here? So look in the picture. There's some function f that's weird and we don't want to understand it, right? So we get an easier function to understand g. And you see g is nicely behaved. And g's down there at the at the bottom one, but then we have g times c1 and we have g times c2, right? Which are constants. Everybody with me here? And you'll see what's happening is, for the most part, f is bounded between them, right? It doesn't drop below the c1 times g, and it doesn't go above the c2 times g, right? It bounds it. Everybody follow that? And that's what this says, right? Everybody can read that, what that says? All right. And then, okay, but for which C1 and C2, right? And I don't care. It could be 1, it could be a billion, it could be a trillion, it could be 0.1, right? Chances are C1 is going to be small, like 0.0001. Now, I don't think I wrote it here, but C can't be 0. All right. So C has, that's why I said it was 0.0001, is because it's got to be bigger than 0. Right. So there's some C1 and some C2, and you got to tell me ahead of time what they are before we play this game. Right? Before I'm going to find out, am I bounded between them, you got to tell me out where I'm, what I'm trying to bound between. Right? Everybody see that? So in the game, if you want to show me that this is the case, you start by giving me the C's. All right, and then what happens? Well, we really want to say, for all sufficiently big N, we're going to be bounded, right? So for every n that's sufficiently big, we're going to be bounded between these two, right? Everybody got that? Now, if you look at the picture, we're not bounded at the beginning, right? For small n, you get to set up the problem. Weird things happen when you have small n, right? There's overhead just to get going, right? So we don't care about small n. Right now, which value of n should we start at? Should we have a rule that n always has to be at least 1,000? No, we don't. People say to me, friends say to me, oh, you're in math, you're good with numbers, right? You know what numbers I know? I know 0, 1, 2, e, pi, infinity, n. Those are the only numbers I know, right? Right, so what is n naught? Well, I'm the prover. I can set any n naught I want, right? You can go out as far as you want, but it's a finite place. And then all n from then on, big n have to be big bounded, right? Everybody good with this definition? The kind of the game. All right. So there's an example. Oh, you see what's happening here is in the slides that I have somewhere else, we went through the example and played the game. But it's more than you guys need. All right? So if you want to play the game, and right off the top of my head, what do you think C1 and C2 should be? 3 and 4, right? 3 and 4. Why 3? Because 3n squared is always smaller than this. Why? Because these guys are positive, right? And why 4? Well, it's because you got to eat this stuff, right? And then what does your n naught need to be? You need to play with it to be big enough so that you can eat this stuff, right? That's about it. Everybody good? All right. Oh, this is just saying one thing I really push when I teach 1090 is the difference between for all exists and exists for all, right? People get that wrong. Let me tell you an example that students get wrong all the time, and it makes me want to torture them, all right? So here, suppose I have a computational problem, and I want to say that the problem is computable, all right? So wish I could write this down. Maybe where can we write this down? No, that's not a thing to write down. Anyway, let me just say it. If I say, for every input, there exists a Java program that solves the problem. Is that good? For every input, there's a Java program that computes my problem. Yeah, it's not good, right? I want to say there exists one Java program that solves the problem for every input, right? And people get that wrong all the time, right? So you really have to be playing the game, right? You see the Java program. Well, you got to tell me the Java program before I tell you the input. You can't make your Java program catering to my input. And how big can your Java program be? Well, you could make it 1 billion lines long. I don't care. But if you make your Java program 1 billion lines long, like for example, your Java program might say, if the answer is 0, this is the output. If the input's 1, this is the output. If the input's 2, this is the output. You could make that your Java program, right? But now I'm going to make the input bigger, right? That's the game. You give me, right? In fact, here's the game. You give me some unreasonably big C, I'm going to just make n not bigger, right? I get to choose, well, I get to choose the N. So you give me a really big C, I'm going to give you a bigger N. Right? Everybody get that? So here, if you were to switch these, this one here is just craziness, right? Because if the adversary tells me what N is, I can find a C2 to make this work, right? Because I know the N, right? It's a whole different game, right? Everybody get that?